Welcome! In this session, we'll tackle an interesting problem from LeetCode, problem number 1233, remove subfolders from the file system. This problem challenges us to efficiently process folder paths and identify a minimal set of root folders, excluding all subfolders. We'll explore various approaches to solve this problem, their trade-offs, and their complexities. Let's get started. In this problem, we are tasked with refining a list of folder paths by removing redundant subfolders. A folder is considered a subfolder of another if its path starts with the other folder's path followed by a slash. For instance, the folder path /a/b is a subfolder of /a, and /a/b/c is a subfolder of /a/b. However, /a is not a subfolder of /a/b. Our goal is to return a list of folder paths that are not redundant, meaning they are not subfolders of any other folder. The result can be returned in any order. The input is a list of strings representing folder paths, and the output should also be a list of strings containing only the non-redundant folder paths. Let's look at the first example to understand this better. Given the input folder list /a//b/c/d/c/d/e/c/f, we can determine which folders are redundant. /a is not a subfolder of any other folder, so it is included. /i/b, however, is a subfolder of /a, so it is excluded. Similarly, /c/d is not a subfolder of any other folder, so it is included, while /c/d/e is a subfolder of /c/d and is excluded. Lastly, /c/f is not a subfolder of any other folder, so it is included. The resulting output is /a/c/d/c/f. In the second example, the input is /a/b/c/a/b/d. Here, /a is the main folder, and both /a/b/c and /a/b/d are its subfolders. Therefore, we exclude the subfolders and keep only /a in the output. For the third example, the input is /a/b/c /a/b/ca /a/b/d. In this case, none of these folders are subfolders of one another. /a/b/c /a/b/ca and /a/b/d are all disjoint, so all of them are included in the output. Now let's discuss the constraints and edge cases. The input list will have between 1 and 10,000 folders. Each folder path will have a length between 2 and 100 characters and will consist only of lowercase letters, digits, and the / character. All folder paths in the input are guaranteed to be valid and unique. For edge cases, if there is only one folder in the input, it will always be included in the result. Similarly, if all folder paths are disjoint, meaning no folder is a subfolder of another, then all folders will be included. The solution must also efficiently handle folder paths with varying levels of depth, such as /a or /a/b/c/d/e. The brute force approach is a straightforward way to solve the problem by comparing each folder path with every other folder path. The idea is to check if one folder is a subfolder of another by verifying if the path of one folder starts with the path of another folder followed by a /. To do this, we iterate through all pairs of folder paths, performing this prefix check for each pair. Whenever we find that one folder is a subfolder of another, we exclude it from our final result. However, this method is highly inefficient for large datasets since it involves nested iterations, leading to a time complexity of O(n²*L), where n is the number of folders and L is the average length of a folder path. Additionally, it requires space proportional to the number of folders to store the results, but the primary drawback lies in its inefficiency for larger inputs due to redundant comparisons and excessive computational overhead. Sorting the folder paths lexicographically provides a much more efficient way to solve the problem. By sorting, subfolders naturally appear right after their parent folders, simplifying their detection. The process begins by sorting the folder paths in lexicographical order. Then, we iterate through the sorted list while maintaining a result list to store the unique top-level folders. For each folder in the sorted list, we check if it is a subfolder of the last folder added to the result list. This is done by verifying if the current folder starts with the last folder in the result list, followed by a /. If the condition is not satisfied, the folder is added to the result list. This approach is significantly more efficient than brute force, with a time complexity of O, n asterisk L asterisk log n, dominated by the sorting step, and a space complexity of O, n, for storing the result list. One of the key advantages of the sorting-based approach is that the sorting step ensures parent folders are processed first, which makes it straightforward to identify subfolders in a single pass. This eliminates the need for unnecessary comparisons and significantly reduces computational overhead. Additionally, this approach is more efficient than the brute force method and is simpler to implement compared to more complex data structures like tries. However, sorting itself can become a bottleneck for very large datasets. Another approach that can be considered is the tree-based method, where a hierarchical structure is built to represent the folder paths. In this approach, each folder is inserted into a tree, and during insertion, subfolders are naturally detected as redundant based on the existing nodes in the tree. While this method is highly effective for detecting overlaps and directly models the folder hierarchy, it introduces additional complexity in implementation and requires more memory due to the tree structure. The tree-based approach offers a unique way to solve the problem by leveraging a prefix tree structure to manage folder hierarchies. Each folder path is inserted into the tree, and as we insert, we check whether the current folder already exists as a top-level entry. If it does, we can skip further insertion since it is a redundant subfolder. Once all folder paths are processed, the unique top-level folders can be extracted from the tree. This method is efficient in terms of detecting overlaps, as it directly represents the folder hierarchy. The time complexity for this approach is O, n asterisk L, where n is the number of folders and L is the average length of a folder path. The space complexity is O, n asterisk L, due to the tree structure, which stores the entire hierarchy. While this approach is efficient, it is more complex to implement compared to sorting and requires additional memory, making it less practical for simpler problem requirements. The sorting-based approach was ultimately chosen as the preferred strategy due to its balance of simplicity, efficiency, and clarity. By sorting the folder paths lexicographically, we leverage the natural order of the paths to detect and remove subfolders in a single pass. While the tree-based approach is slightly more efficient in some specific cases, its additional complexity in implementation and debugging makes it less ideal for this problem. The sorting-based method, on the other hand, is easy to implement, understand, and debug, making it a practical choice for most scenarios. When comparing the approaches, brute force is infeasible for large inputs due to its poor performance, while sorting strikes a good balance between computational efficiency and ease of use. This trade-off makes it the most suitable solution for typical problem constraints. The key insight that unlocked the solution was realizing that sorting the folder paths lexicographically groups subfolders immediately after their parent folders. This eliminates the need for more complex hierarchical constructions, such as in the tree approach, and avoids the redundancy of nested comparisons seen in the brute force method. By leveraging this natural order, we can efficiently remove subfolders in a single pass through the sorted list. The final complexity for the chosen method is O, n asterisk L asterisk log, n, for time, with sorting dominating the process, and O, n, for space to store the result list. This approach is both efficient for realistic input sizes and straightforward to implement, making it an excellent solution for the problem at hand. The goal of this problem is to identify unique folder paths from a list of directory paths, ensuring that no folder in the output is a subfolder of any other folder. For instance, if we have the input list /a/b/c/d /c/d/e/c/f, the output should be /a/c/d/c/f. This is because /a/b is a subfolder of /a, and /c/d/e is a subfolder of /c/d, so they are excluded. To solve this, we start by sorting the folder paths lexicographically. Sorting organizes the paths in dictionary order, which ensures that parent folders always appear before their subfolders. For example, /a comes before /a/b, and /c/d comes before /c/d/e. This ordering is critical because it allows us to process parent folders before their subfolders, making the subsequent steps more efficient. Then, we initialize an empty list called result to store the unique folder paths. This list will be built incrementally as we filter out subfolders during the next steps. Now, we iterate through the sorted list of folder paths. For each folder, we check whether it is a subfolder of the most recently added folder in the result list. This is done by verifying if the current folder starts with the last folder in result, followed by a /. This condition ensures that only direct subfolders are excluded. If the current folder does not meet this condition, it means it is not a subfolder and can be safely added to the result list. By only comparing each folder to the last added folder, we avoid redundant checks and achieve a highly efficient approach. After completing the loop, the result list contains only the unique parent folders, which we then return as the output. This approach works because sorting ensures that parent folders appear before their subfolders, and the prefix condition allows for a quick determination of subfolder relationships. Additionally, building the result list incrementally ensures that it is always up to date and contains only the valid parent folders. To implement this solution, we use simple yet effective data structures. The input list itself is processed directly after sorting, and no additional storage is needed for intermediate states. The result list is used to store the final output, and it dynamically grows as we add parent folders. When analyzing the complexity, sorting the folder paths is the most expensive step, with a time complexity of O(n*log n, where n is the number of folder paths. Iterating over the sorted list and performing the subfolder check for each folder is linear, with a time complexity of O(n). Combining these, the overall time complexity of the algorithm is O(n*log n). In terms of space, the result list requires O(n) space in the worst case, where all folders are unique and no subfolders exist. This makes the algorithm both time and space efficient, suitable for handling large inputs. There are several edge cases to consider for this problem. If the input list is empty, the result should also be an empty list because there are no folders to process. If there is only one folder in the input, the result will simply be the same folder since it cannot have any subfolders. For scenarios with deeply nested folders, such as /a/b/b/c, only the top-level folder /a will remain in the result because all other folders are subfolders of /a. The sorting step ensures that the algorithm handles unsorted inputs correctly, as the lexicographical order places parent folders before their subfolders. Let's walk through the example input /a/b/c/d/c/d/e/c/f. After sorting, the list remains the same because it's already in lexicographical order. We initialize the result list as empty. Then, we iterate through the folders, /a is added to result, /a/b is skipped as it is a subfolder of /a, /c/d is added, /c/d/e is skipped since it is a subfolder of /c/d, and /c/f is added. The final result is /a/c/d/c/f. This Python solution solves LeetCode problem number 1233, remove subfolders from the file system efficiently by leveraging sorting and prefix matching. ###explanation. 1. Sorting the input. The folder paths are first sorted lexicographically. This ensures that potential parent folders appear before their subfolders in the list. For example, /a will appear before /a/b and /ac. Sorting is done using Python's built-in sort method, which operates in O(n*log n time. 2. Initialize the result list. The first folder in the sorted list is guaranteed to be a top-level folder, so we add it to the result list immediately. 3. Iterating through the sorted folders. Starting from the second folder, we check if the current folder is a subfolder of the last folder added to the result list. This is done using the starts with method. The condition folder, i.starts with result-1 plus / ensures that only subfolders, with a / delimiter, are excluded. 4. Adding non-subfolders. If the current folder is not a subfolder of the last folder in result, it is added to the result list. This ensures that only unique top-level folders are included in the final output. 5. Return the result. After processing all folders, the result list contains the required top-level folders, which is returned as the output. ### complexity analysis. Time complexity, sorting the folder list takes O(n*log n, and the single traversal of the list takes O(n). Thus, the overall time complexity is O(n*log n). Space complexity, the solution uses O(n) space for the result list. This implementation is concise, efficient, and handles edge cases such as empty input or single folder input gracefully. This is the Java implementation of LeetCode problem number 1233, remove subfolders from the file system. The logic mirrors the Python implementation by first sorting the folder paths lexicographically, then iterating through the list to ensure that only top-level folders are added to the result. Key differences include the use of Java's list and arrays.sort for handling collections. Additionally, type declarations are required for variables and methods in Java. In this example, we need to remove subfolders from a given list of folder paths. The input is a list of folders, /a//b/c/d/e/c/d/e/c/f. The first step is to sort this list lexicographically. Sorting ensures that any subfolder will appear immediately after its parent folder, which makes it easier to identify and skip subfolders. After sorting, the list remains the same because it's already in lexicographical order, /a//b/c/d/e/c/d/e/c/f. Next, we initialize a result list with the first folder in the sorted list, which is /a. This result list will eventually contain only the folders that are not subfolders of any other folder. Now, we iterate through the sorted list of folders to determine which ones to include in the result list. Starting with /a//b, we check if it is a subfolder of the last folder in the result list, which is /a. To do this, we verify if /a//b starts with a, and it does, so /a//b is skipped. Next is /c/d. Checking against the last folder in the result list, /a, we see that /c/d does not start with a. This means /c/d is not a subfolder of /a, so we add /c/d to the result list. The process continues with /c/d/e, which starts with /c/d/, indicating that it is a subfolder of /c/d. Therefore, it is skipped. Finally, we evaluate /c/f. It does not start with /c/d/, so it is not a subfolder of /c/d. We add /c/f to the result list. At the end of this process, the result list contains /a//c/d/c/f, which is the final output for this example. Here, we look at a simpler case where the input contains only one folder, /home. Since there is only one folder, no sorting is required. We directly initialize the result list with this single folder, resulting in /home. With just one folder in the input, there is no need to iterate or perform any checks for subfolders. The result list remains as /home, which is also the final output for this example. This demonstrates the simplest case of the problem, where the input does not contain any potential subfolder relationships. Next, we examine a case with nested subfolders and an additional unrelated folder. The input is /x/x/y/c/x/y/a/b. We start by sorting the list lexicographically, which rearranges the folders to /a//b/x/x/y/x/y/c. Sorting ensures that subfolders are grouped with their parent folders and appear immediately after them. Once sorted, we initialize the result list with the first folder, /a//b. This folder is guaranteed not to be a subfolder of any other folder because it appears first in the sorted order. We now iterate through the sorted list to identify which folders to include in the result list. Starting with /x, we check if it is a subfolder of /a//b, the last folder in the result list. /x does not start with /a//b/, so it is not a subfolder, and we add it to the result list. Next is /x/y, which starts with, indicating that it is a subfolder of /x. As a result, /x/y is skipped. The same logic applies to /x/y/c, which also starts with a, marking it as a subfolder of /x. Therefore, /x/y/c is skipped as well. At the end of the iteration, the result list contains /a//b/x, which is the final output for this example. This illustrates how the algorithm handles nested subfolders and unrelated folders efficiently. The time complexity of this solution involves two main steps: sorting the folder array and iterating through the sorted list to remove subfolders. First, the sorting step arranges the folder paths lexicographically. Sorting a list of strings with a total length of L takes O, L * log, L, time. Here, L is the sum of the lengths of all strings in the folder array, which equals the number of folders, n, multiplied by their average length, m. This makes the sorting step O, n*m*log, n*m. Next, the algorithm iterates through the sorted list, starting from the second folder. During the iteration, it checks if the current folder starts with the last folder in the result list followed by a slash. This check uses the starts with method, which compares strings character by character and takes O(m) time in the worst case. Since there are n folders, the total time for this iteration step is O(n*m). Combining these two steps, the sorting process with its O(n*m*log, n*m) time complexity dominates the iteration step, which has a complexity of O(n*m). Therefore, the overall time complexity of the solution is O(n*m*log, n*m). Now, when we analyze space complexity, the input folder array must be stored in memory. Since the total size of the array is proportional to the sum of the lengths of all folder paths, this requires O(n*m) space. Additionally, the sorting process typically uses extra space for managing pointers, which adds O(n) space. However, the string content is part of the input storage, so it does not contribute additional overhead. Beyond input storage and sorting, the algorithm also allocates space for the result list, which stores the top-level folders. In the worst case, where no folder is a subfolder of another, all n folders are added to the result list, requiring O(n*m) space. Besides this, only a few temporary variables are used during iteration, which take constant space, O(1). When we combine all these components, the total space complexity is determined by the input folder array and the result list, both of which are O(n*m). Comparing this solution to a brute force approach, a naive method would compare each folder with every other folder to detect subfolders, leading to a time complexity of O(n²*m). By sorting the folders first and performing a single pass to check subfolders, this solution reduces the time complexity to O(n*m*log, n*m), making it significantly faster, especially for large inputs. Now, let's look at the best, average, and worst-case scenarios. In the best case, where all folders are top-level and none are subfolders of another, the algorithm still needs to sort the folder list and iterate through it, resulting in a time complexity of O(n*m*log, n*m). Similarly, for an average input, where some folders are subfolders of others, the complexity is still dominated by the sorting step, so it remains O(n*m*log, n*m). Even in the worst case, where all folders are deeply nested, the sorting step continues to dominate, ensuring O(n*m*log, n*m) as the overall complexity. To mathematically justify this, sorting requires O(l*log, L operations, where L is the total length of all folder paths, or n*m. Meanwhile, the linear iteration step, with its O(n*m) complexity, is asymptotically smaller. For space complexity, the memory required is primarily for storing the input and output lists, which scales with the total size of the folder paths, O(n*m). The algorithm is well optimized compared to a brute force approach, making it highly efficient for handling large datasets with nested folders. When tackling this problem, there are a few common mistakes that can lead to incorrect results or inefficiencies. First, ignoring sorting when working with hierarchical problems is a critical error. Sorting the folder paths lexicographically ensures that parent folders always appear before their subfolders, making it easier to correctly identify relationships. Without sorting, you might end up performing unnecessary checks or misidentifying parent-child relationships, which can lead to incorrect answers. Next, relying on simple string matching without accounting for delimiters can cause false positives. For instance, checking if a folder starts with another folder's path without verifying that the next character is a delimiter, like a /, could result in errors, for example, treating folder 1 as a parent of folder 10. Lastly, brute force approaches that use nested loops to compare every folder against every other folder are highly inefficient. Since this results in O(n²) time complexity, it can quickly lead to time limit exceeded errors, especially when the input size is large, such as 10,000 folders or more. Another frequent pitfall is neglecting to manage edge cases properly. It's important to handle scenarios like duplicate folder paths, empty input, or inconsistent formats where some paths might have trailing slashes while others do not. Overlooking these situations can lead to runtime errors or incorrect results. Additionally, overcomplicating your solution by using unnecessary extra space is a common mistake. For instance, building a complete tree representation of the folders may seem intuitive, but it often increases space complexity without providing significant benefits. A simpler approach that avoids such auxiliary structures can achieve the same result more efficiently. Keeping these points in mind helps you avoid unnecessary complexity and ensures your solution is both correct and optimal. Now, let's dive into some useful insights, especially for interviews. A key pattern in problems involving hierarchical relationships, such as folder structures, is the importance of sorting. Sorting lexicographically by the folder hierarchy is often the first optimization step and sets the stage for an efficient solution. Your goal should be to achieve an n*k solution, where n is the number of folders and k is the average folder path length. Efficiency is crucial, as brute force solutions will not suffice for larger inputs. Additionally, always consider edge cases, whether the input can include duplicates, empty lists, inconsistent formats, or deeply nested structures. Clarifying the problem scope with your interviewer is pivotal. For example, ask whether trailing slashes or duplicate paths are allowed, as this could influence how you pre-process the data. If you're preparing for similar problems, you might explore related challenges like LeetCode 721, which deals with merging accounts, or LeetCode 588, which involves designing an in-memory file system. These problems provide valuable practice for handling hierarchical data effectively. Finally, let's explore some alternative approaches to solving this problem. One of the most straightforward methods is sorting-based. By sorting the folder paths lexicographically, you can iterate through the list while keeping track of the current parent folder. Any folder that starts with the current parent can simply be skipped. This method achieves a time complexity of n*k plus n*log n, making it both simple and efficient. Another option is using a tree data structure. Here, you insert each folder into the tree, and if a folder is already represented, you skip adding it again. The tree provides a structured way to manage the hierarchy, but it requires extra space, which may be unnecessary for simpler problems. Lastly, there's the union-find approach, where folders are treated as nodes, and subfolders are unioned with their parents. Path compression optimizes this process, though it adds some complexity. While union-find is particularly useful for problems involving connected components, it might not be the best fit for this specific problem. Choosing the right approach depends on the problem constraints and your familiarity with these techniques. Thank you for joining me on this walkthrough of problem number 1233, Remove Subfolders from the File System. We reviewed multiple strategies, their trade-offs, and the importance of leveraging data structure properties for optimization. I hope you found the explanations clear and insightful. If you enjoyed this session, don't forget to like, subscribe, and stay tuned for more exciting problem-solving sessions. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!